So we're going to kind of buzz through this. So again, remember I put, these are my notes that are online. So you can print them out ahead of time if you like to have a structure or you want to see kind of where we're going. I don't have everything solved in here. This is sort of my outline, but at least you'll know what we did in class. Okay, so let's start with this. There's basically a big difference between this and this. Talk about this notation. This is function notation. It means put in a value of c everywhere you had an x. So this is an exact value, if it exists, right? This is a point. This is limit notation. Am I taping?
Yeah.
Yeah, okay. Sorry. This is limit notation, which says, as x gets closer to c, where am I headed?
To a point.
Maybe, or maybe not. But the question is, where am I headed? What is my trend? Where am I going? Does any of that sound like exact value to you? No. So this is about behavior. So that's the key thing to remember about limits, this versus this. They're both y values. Let's be clear. These are both y values. This is the exact y value of the function at x equals c. This is, where's x going? Where's it aiming toward? Because we've all done this in real life, right? You're headed off somewhere, you're going somewhere, and all of a sudden you get there and it's not where you thought you were going, right? The path is this, the limit. So let's do a couple of examples. So y equals x squared. What is f of 2? Y equals f of x. What's f of 2? Just plug in the 2, right? We get 4. So f of 2 is 4. So that point is right there. If I want to, when I want to look at the limits, sometimes what I do, either in my mind or actually on the paper, that is, everyone agrees that's not an asymptote, even though we draw asymptotes that way. It's not an asymptote, so it went right through the graph. Now this is saying, the limit says, well, as I get close to 2, get on this function. If I'm going this way, am I getting close to x equals 2?
No.
No. So I'm going to follow this function, and I'm going to stop when I get to my line. I'm going to follow this function, I'm going to stop when I get to the line. Where's the function headed?
Towards 2.
Towards x equals 2 and towards, is it
4.
headed towards y equals 4? It's
Yeah.
headed to exactly that point. So this, the limit as x approaches 2 of f of x. There is a lot of writing in limits. I apologize for that. There's no way around it. You must write it. This is also 4. They're the same. So what happens if I do this? I put a hole right there at 2, 4. Does this value still exist?
No.
No, right? Does not exist. Let's go ahead and introduce that. If you haven't seen that before, that is short for does not exist. It is not defined because there's a big old hole in the graph.
What exactly is the hole in the graph, though?
It is
Never
it's
quite
as,
understood that.
a hole in the graph is as if you just could literally pull a point off and just say, not that one. And so,
It's like everything included, but not this number.
yes, it's kind of like the difference between this and this in interval notation. This one includes the point, and this one does not. So this is getting all, so if we were to write the domain for this,
Right.
it would be negative infinity to 2, together with 2 to infinity. Everything except that exact one point. Yeah. So, but here's a question. So the point no longer exists. What about the limit? What's the function doing? Cruising on, cruising on. Did the function behavior change? So is the limit still 4?
Yeah.
Yeah. So, interestingly, the limit might equal the value or it might not. What if I do this? What if this point that's at 2, what if I really define it to be right here? So that point, this is a piecewise function. So I would write it this way. I'd say that this is equal to x squared as long as x is not equal to 2. So it looks like x squared everywhere. But when x is equal to 2, I'm going to just say it's 2. I just picked it out of the air. So now here's a question. does f of 2 exist?
Mhm.
For part of it.
Well, f of 2, that says, well, it's not this one, it's this one. So when x is 2,
At two.
f of 2 is 2. So now, this one that used to be 4, and it did not exist when we had the whole, but now we've redefined it, so now this one is now equal to 2. Has the limit changed? The function's still doing this, the function's still doing what it's doing, right? It's cruising along, cruising along. It's about behavior. So whether the point exists or not, whether the point's where I want it to be or not, does not change the limit. The limit is all about what is the function, where's it headed? What's the direction? Okay. So these are what limits are. Okay, so let's write a couple of things. We're going to call this a behavior, but we're also going to give it a number if we can. So in this case, this limit was equal to 4. The behavior is it's going to 4. This may or may not equal this. It might or might not. So it could equal it, or it might not equal it. They are not related in some sense. The actual point is what it is. Behavior is what it is. They may match and they may not. And if they match, that'll be important for us later. All right, so let's look at, now, so far this looks like kind of a nice function, right? It's a parabola. We know what parabolas do. They just, you know, all polynomials, right? They just do their thing, nice and smooth and easygoing. What happens if we have a piecewise function? So let's look at this. And feel free to ask questions in the middle, and particularly, please, as I've said before, make sure to correct any mistakes I make before I get too far. All right, so now we need to define some other things. We need to look at what we call sided limits. So let me give you an example of a function where we're going to need it. Okay, so this is at 1, -1. For those of you who are interested where this came from, that is the slope of the absolute value, right? Slope is 1 here, it's -1 here. I don't know what it is there because it could be, I don't know what that is because I'm at a point, I don't know what it is. So that's just where that comes from. Okay, so here's a question. What is the limit as x approaches 0 of this function? Can I give an answer to that?
Depends which way you're going.
It depends which way you're going, right? If I'm coming from this way, I'm doing one thing. If I'm coming from this way, I'm doing a different thing. So that's where we need to define sided limits. So we have a right-sided limit. And we indicate that by a plus sign. I'm coming to the value from the plus side, the right side. And we have left-sided limits. What do you think we're going to use for that?
Or L.
Well, or a
Minus.
minus sign. Yeah. So we're going to say limit as x approaches c from the negative side.
For that one though, wouldn't it be from both sides because you're not illustrating plus or minus?
Correct. So this is a two-sided limit. So two-sided limits have no plus or minus on it, right and left side. So two-sided limit, right, correct, has no, it's this one. Okay, so let's look at this. I can't answer the two-sided limit. The sides are different. So let's talk about the right-sided limit. If I want to look at this from the right side, I'm on the graph. I'm headed towards x equals 0. Where am I headed for y?
1.
Remember, it's the y value. So I'm up at y equals 1. So here's my x value. That's the x value from your limit. Now just get on this, and as soon as you get to that dotted line, stop and look at your y value. So the y value is 1. If I do the same thing on the left side, I cruise towards that dotted line, I stop when I get there, what's the y value?
-1.
-1. Okay, so, yes?
For the two-sided value would just be does not exist, right?
Correct. Got this much ahead of me, exactly. So here's the problem. I can always look at a right side and a left side, right? I could do that with a parabola from the right side and from the left side. They just happen to be going to the same place. So that two-sided limit existed, no problem. So here, this two-sided limit, we say does not exist because they are not the same. The right-sided limit does not equal the left. And that's a shorthand that I use. It's very casual. This is like text talk in math. So normally you would say, this one does not equal this one, or the right-sided limit does not equal the left-sided limit. So I will know what you mean if you write that. But that is the reason. Because I don't, which one would I pick? No, there's no way to pick, yeah.
Is that always the case that the left will never equal the right?
No.
Or is there a case where it can equal both? I never saw that one. Okay.
Right, so here's the one we just did. If we come from the left or we come from the right, go to the exact same spot. Okay, so in this case, the right and the left do agree, so the two-sided limit does exist, and we found that. Right. So this is for cases where, we're going to get back to this when we look at things with asymptotes, because clearly with asymptotes, you might not, right, do the same thing on either side of the asymptote. Typically, polynomials are well-behaved. Okay, so let's talk about then let us look at, I'm kind of redoing the prep video, which was not my intention, so I won't do that next time, just so you know, I'm not doing this again, because this is taking away from the time to do harder things. So let's look at, a couple of other rules that we need to have. So these are laws of limits, or limit properties. I'm going to write them in English. The limit of a constant. If the y value is always 2, where's the y value going? Can it go anywhere else? No. So the limit of a constant is equal to a constant, whatever that constant is. So the limit of 2 is 2. The limit of a sum, just add up the limits. You can treat them separately. Same with the difference. So if you add or subtract, then you just, basically just, all of the math that you know how to do with algebra, when you're putting in values, every calculator thing that you know how to do works with limits. So you can, the limit of a product, you've got two things multiplied together, you want to find the limit, you just multiply the two individual ones. What about dividing? The limit of a quotient, will that work? So long as you're not dividing by what?
0.
0, right? So limit of a quotient, a fraction, that's no problem. It just says divide, but be careful with not dividing by 0. So let's just do some examples. I'm going to leave those there for a minute. And let's do this one. So here's the limit. So the first thing you're always going to try when you do limits, the first thing you will always try for every limit problem you're going to do is plug in the value and see if you get something that makes sense. So let's do this one. This is example 6 from the notes. So limit as x approaches -1, x plus 1 over x plus 2. I'm going to plug it in. See if anything good comes from it. So if I put in -1 in the top, I get 0. -1 in the bottom, I get 1. 0 divided by 1. I know that sounds like a silly question, but it's not. 0 divided by 1 is? It's 0. 0 divided by anything is 0, except, we're going to get to that shortly. 0, there is a problem one time, but if it's 0 divided by a regular number, the answer is 0. So this limit is 0. Done. That's it. Okay? If you plug in the number and you get a number that makes sense, you're done. Okay, so let's try another one. Let's try this one. Limit as x approaches -5. You can also square root. So the limit of the root just says do the root. So the limit of the square root of -5x plus 11. Plug, yes?
So I was taking notes while you were
Yeah.
talking. I don't know how you get to 0 over 1.
I plugged in.
Oh, okay. Gotcha.
Yeah, so the first thing you always do is plug in. Whatever your value is for your limit, plug it in. If you get something that makes sense, you're done, that's it. So we always try that. So what about this one, -5? -5 times -5 is 25, 36, square root of 36 is 6. So this is that a number that makes sense? Okay, done. Okay, so that's the first thing you always try. So now what about this one? Oh wait, before we get there, let's do one more, because that was an example, I don't know what numbers I'm on, I don't think my numbers added up right. All right, so here's another one. What if you have, so this is example 7, what if you have this? X squared plus 2, a piecewise defined function. I'll give you a minute to write that down. So x squared plus 2 and 4x minus 1. So if I look at the limit as x approaches 2, piecewise defined function says I have 2 different ways to define it based on whichever piece, in this case 2 ways, based on the pieces. So if I am interested in x going to 2, which of these pieces will I use?
4x minus 1.
So everyone see that this is the piece that contains my point of interest, so this is the definition I'm going to use. Yes?
I didn't get that.
So I have defined this function 2 ways. If x is less than 1, it looks like this. If x is greater than or equal to 1, it looks like this. So if I'm interested in x going to 2, which of these categories does that fall in? This one. So that means I'm going to use this definition. Okay? So then this would be the limit as x approaches 2 of 4x minus 1. Plug in. Is that a regular number? Yep, good. Okay, so now let's look at, obviously, what's the interesting point in this problem? What x value is going to give me the most interesting thing to talk about? 1, exactly. So let's look at that. So let's look at limit as x approaches 1. Technically, 1 is in this one, right? So I can find f of 1. I know what it is. Let's write that out. F of 1 is just, I use this definition because 1 is in this category, right? Greater than or equal to 1. So 4, what was that, 3?
Yeah.
But now the limit means I'm looking at it as I'm approaching. Is this a one-sided or two-sided limit?
Two-sided.
Two-sided. So I actually have to look from the right and the left. So I need to write out separate limits. So let's look at that. Let's come over here and write out separate limits. So anytime you have to look at a two-sided limit, you need to write that out separately. Yes?
How do you know it's a two-sided?
Because there's no plus or minus sign on it already. Yeah. So I'm going to write the right-sided limit.
So how come the last one wasn't a two-sided? Because you didn't verify your anything.
Well, because this is right in the middle, there's no, I could have broken this apart into left and right side, but this is just such a nice function that it's,
Okay.
there's
So
no reason.
because it's like right at 1, that's why.
Yeah, because this one is right at the break point, I have to, the two sides are defined differently. This one, 2, was right in the middle of a piece, and I had no reason to expect anything would go awry. But here, left and right are going to look different. So from the right-hand side, I'm going to pick this one, right, from numbers bigger than 1. So it will be this. The left side, I need to go where it's slightly less than 1. Where is that? That's going to be this one. So now I have to use this definition. So because I'm interested in the breakpoint between the pieces, I have to use one definition on one side and one definition on the other side. Does that mean they won't agree? No, they might still line up. I just have to check them separately. Okay, so now plug in 1. What do we get?
Well, there's x squared plus 2.
You're right, thank you. So plug in 1, I get 3. Plug in 1, I get 3. Does that two-sided limit exist? The right and the left go in the same places, so yes. So this two-sided limit does exist. Did I know that in the beginning? No. You cannot know that a two-sided limit exists unless you know the right and the left match. In this case, here, any of these, I plug in a number, there's no reason to expect anything weird to go wrong. So these I don't have to break them apart. But this one, when I'm interested in the breakpoint, I don't know that they're gonna line up. So you have to test them. So anytime you have a two-sided limit that looks like there could be a problem, you have to look at right and left separately. Okay, so let's look at this one. So I know it seems, yes, 0 divided by 1 is 0. What about this one? First thing you always do with limits is what? Plug in. So I plug in 1, and I get 0 over 0. Okay, so no, wait. 0 over a number is 0, right? So I know that 0 over any number is equal to 0. But I know that any number divided by 0 is what? That blows up, right? That's going to infinity. So which one's that?
0.
Or anything in between. We don't know what that is. That seems kind of weird. Anytime you get 0 over 0, we don't actually know what that is until we do more work. This is called an indeterminate form. Indeterminate form, 0 over 0. You get 0 over 0 and you should say, okay, more work. That's with it. So it's not 0, it's not infinity, we don't know what it is until we do more work. So let's take a look. Let's graph this. It looks like it's a mess to graph, but not really. What's the first thing you always do when you're graphing a rational function? You want to factor things, see if anything, you get lucky, see if anything cancels. So if we look at this one, does that factor? Does any part of that factor? Right?
Yeah.
The numerator does nicely. So we'll get x plus 1 times x minus 1 all over x minus 1. Do I see any other goodness that happens? Yeah, multiplied factors. So this is equal to x plus 1, except not where x is equal to 1, right? That was part of my original domain, whether x could not equal 1, so I have to keep that. So this is a line with one point that's not on it. And so this gets to Tori's question. When there's one point that's not on it, what is that? Hole in the graph, right? There's that one point, it looks like a line the whole way. It goes through here, it's got a slope of 1, except right here, at x equals 1, there is no point. It's not in my domain. So it looks like a line, except one point pulled out. So it's a hole in the graph. So let's think about this. We can answer this limit then graphically. I'm looking for x equals 1. I'm going to follow the graph until I get there. When I get to this point on the line, I look at what the y value is. What's that y value? So in this case, the limit, this 0 over 0 equals 2. Does that seem weird? So 0 over 0, you don't know what the value is. 0 over 0 indicates that you have a term that's going to cancel. A term that cancels is a hole in the graph. So do I need to do this graphically? No. I need to do this part though. So if I go to solve this problem, so let's lay this out.
So how is it touching the y-intercept of 2? Or how is it aligned with that y-intercept of 2?
Because this is a graph of the line y equals x plus 1. So when I get to x equals 1, I know the graph is going to be at y equals 2. So x equals 1, y equals 2. So you can do it graphically. So the thing to drive home is that 0 over 0 is indeterminate. You don't know what the answer is. But for our class, it will represent a hole in the graph. It will. So the more work you need to do is factor and cancel. You can graph if you want to and graph the hole, or you don't have to. Okay, so the more work here, factor, cancel, and then you can just substitute the value again. You can graph if you want to, but you don't have to. So let's back this up and start this problem again without all the explanation and just look through the process. Is that okay? All right, so I'm going to erase, but I'm going to rewrite it. Okay, so here I'm presented with this problem. What's the first thing you always do?
Plug in.
Plug in. So I plug in, I get 0 over 0. I immediately say to myself, aha, that's an answer that I don't know until I do more work. So the more work I need to do, and you can keep writing the limit signs. That's really probably the best thing. I'm going to factor. I'm going to cancel. I know that the offending 0 in the denominator is the thing that's going to cancel. If it doesn't, then something didn't go right. And so now this is equal to the limit as x approaches 1 of x plus 1. What's the first thing you do when you have a limit? Plug in 1, 2. So what does this represent? This represents a graph. So you need to equate this also. This is a graph of y equals x plus 1 with a hole at x equals 1. And do I know the y value of it? That's that limit, right? Where's the function going to? Where the point would be if I didn't pull it out? Y equals 2. So these two go together. So first order of business, always plug in. The second piece we learned today is 0 over 0 means hole in the graph. Factor, cancel, do it again. Any thoughts on that? You want to try one? Yes. All right, so let's try. Let's try this one. And we'll do this a lot in class where I'll set one up and I'll say, go ahead and work on it with the person next to you, or work on it by yourself. If you finish early, take a look around, see if anyone else needs some help kind of working through it. And so what I'll do is I'm going to pause this here.